Hi everyone, I'm going to start my talk on alternative concurrency models if anyone's interested. Thank you. Okay, right. People filter over. I'll start in a sec, yeah.
You point it to the left and then you step your legs potentially.
Cool. Okay, stand here. Right. Hello everyone, thanks for coming to my talk. This is about different ways of looking at concurrency in software, as opposed to just using threading, which I find quite confusing. So a little bit of backstory about me. I'm Charlie. I came from a C background. I did robotics at uni, so I found object-oriented programming and threading quite hard to get my head around at the start. So this is a little bit of what I prefer to use day to day. So why use concurrency? Processors aren't getting that much faster anymore, but what you are finding is you're getting a lot more cores. Like you can get this Knight's Corner from Intel, which is 64 cores now, a lot of cores, but the speed of the processors aren't actually going up at all. So how do we leverage this? So first of all, I'm just going to explain a little bit about what concurrency is with an interesting example. I don't know if anyone here watches Game of Thrones. I do, and so does my girlfriend, and somehow she manages to text her friends while watching it. I don't really understand that because it's quite a lot to take in. So something that's a more traditional program model would be a kind of a procedural synchronous model. So it would be, I'll watch some TV, that will block the phone operation, and then I'll play Angry Birds afterwards. So that's my kind of model when I'm watching Game of Thrones. But my girlfriend somehow manages to do a bit of both. So a concurrent way would be they're completely separate tasks now. So I can watch TV, and in the adverts, I'm going to play some Angry Birds. So this would be asynchronous and interleaving as she's doing both still. Parallel would be watching Game of Thrones with one eye while playing Angry Birds with the other, which is something she manages to do. This is asynchronous, but this time it's not interleaving, they're running in parallel. And then finally, a distributed way of doing this would be getting me to play Angry Birds while she watches the TV. That would be non-cohabitating processors way of watching Game of Thrones. So concurrency is a great tool, and there's loads of different ways to do it, and there's not, I want to put across in this talk, there's not a right way, there's not like a golden path or a silver bullet. You've really got to find the best way for each task. So the traditional way, and I'll kind of whiz through this way, is threading. It's by far the most common and popular method. It's the traditional old-fashioned way of doing it, and personally I find it really quite confusing. So this is a picture of kind of a picture representation of threading. I'm sure if most of you guys have done some programming, which I guess you all have, you kind of understand this already, so I'll whiz through it. There's lots of problems with threading. I find it hard because of things like shared memory, data races, deadlocks, priority inversion, heavily contested lots, and obviously once you have a massively multi-threaded something like C++ program, it can be really a minefield to edit any one part of it without breaking another. So let's have a look at some other models. So the actor model, this is probably my favorite because it's so easy to get into and use. Instead of having objects, everything is an actor. So an actor would be an object, but it has a small, it has a buffered mailbox, and everything is done through messaging. The messages are asynchronous, so you can send as many messages to a mailbox as you want, and when an actor receives a message, it will set off a behavior. So it might, I don't know, send a message to another actor, it could spawn new actors, it could do some kind of transaction on its internal memory. The important thing to realize about actors is there's no shared memory. Each actor contains all the memory it requires, so you're never going to be locking or waiting for other actors. And the real life analogy of this would be like sending mails to people where everyone is a actor. So it's non-blocking, you can get loads of mails at once and you just sort through them. And this
it's still a deadlock, couldn't you? Because I could be waiting for another actor who was waiting for me.
Not exactly, because everything is done through mails.
Yeah.
if you don't get the mail, you don't do the work.
Yeah. Okay.
So an actor could block another if you're waiting for a series of events to happen, but it doesn't block in the sense that you're waiting for a memory location to become available. That would be more of a problem with your program, the program design and the memory. So this is kind of a picture representation of what that might look like. So messages pinging to and from actors, and the thing to remember about messages is every message can be any type in the message, but it also always has to contain the sender's address. Actors don't have a list of every actor available, so the main way of communicating is either through an address directory or through the recipient address of a mail. So in the title I put about Halo, so I think I'll talk about a little bit about that now. So spelling mistake there as well. Halo 4 uses this thing called the Orleans framework, which is an actor system. So they have about 11 million players on a good day, and I think they've had about 2 billion games now, and they have to store this somehow. Players will go onto their service and they want to see their statistic analysis of the player, how many kills, how many deaths, things like that. So they use this thing called Orleans. So you've got a front end where the player might do a HTTP request for something like how many headshots have they had in the last 5 days or something, I don't know. And every player is an actor, or they call it grains here, and every game is a grain. So basically every request is non-blocking, which is really nice because you might want to look at a game of 64 players. That means there's 64 possible places where you might have had to lock a memory location previously, but with this model, you don't have to worry about that. So the typical kind of request looks something a bit like this. So your Xbox will do a series of HTTP requests to a game grain. The game will have just finished and have things like the amount of kills, the amount of players, what map type, and then this will send messages to the player grains, how many kills they got in that, did they win, did they lose, what map was it, and this will all be stored in the player grains, and then the player grains will send back a message to the game telling the game it can now go and kill itself, put itself in storage, and that's kind of the process. So why bother doing it this way? Why not just have a massive table of players and games? Well, on a game launch, you don't know how many players you're going to get, so it needs to scale really well, and it needs to scale in a distributed way. So here we have a performance analysis. So each one of these throughput requests would have been a single request to up to 2 or 3 grains, so it's quite substantial. So you can see here that it scales reasonably linear, and you're getting a lot of performance throughput for the number of servers. And here you can see the number of actors actually scaled relatively linear as well. What you're seeing here is the memory is actually becoming full. So if you were to add more machines at that point, then the number of actors scales kind of in a flat way, which is the performance you want to see. So yeah, actors are great because you've got a high level of abstraction. Each actor is effectively single-threaded application, so your programmers don't have to worry about threads or data states, anything like that. You don't see any race conditions, deadlocks or anything, and it's very easy to distribute. You can just spin up an actor on any machine as long as you have the address of the actor. But it's not great because obviously shared state is often required. Synchronous behavior is obviously needed quite a lot as well, and the buffered mailboxes of each actor can be massive if your performance is rubbish. So let's have a look at another model, which is one I've started using a lot since I'm programming with Go, which is CSP, communicating sequential processes. So it's basically the actor model, but there's no mailbox. So when I send a message to one of these actors, it has to be ready to receive it. So it actually synchronizes the program, which is actually quite useful in some cases, because message passing naturally synchronizes threads. And the real life analogy of this would be you ring someone up, they've got to pick up to receive the message, as long as there's no answer machine. So I've got some code examples, I hope it work. So this is Go, in case you haven't seen it before. So what I'm doing here is basically spinning up a Go routine, which is you're putting a function into its own thread and letting it do its own thing. And here, instead of mailbox, it's called a channel. So a channel is just a single location in memory where that piece of information can be shared across the actors. So what I'm doing here is I'm declaring a channel at the top called channel. In the function main, I'm saying I want the function hello world to go in its own Go routine, which then basically puts hello from a Go routine into the channel. And then in the main thread, I'm saying check that channel and put it into the string called message and then print that out. So hopefully we'll see that work. Yeah, so there we go. So not the most exciting demo, so let's have a look at this one. It's a little bit more involved. So here we've got two different functions that are going to be called as Go routines, so in separate threads. And all they're doing here is playing a game of ping pong. One's putting a message into the channel, the other one's waiting for that message, so it's blocking it. Once that message is in there, the other one can receive the message and carry on, and then it itself puts the message in there and it's going back and forth. Hey, it works. The gods of demo have smiled upon me today. So CSP in practice, there's not actually many examples of this at the moment, but there is one massive one, which is most downloads from Google go through dl.google.com, which is completely written in Go and only with the standard library. So that talk there is fascinating about how they did that. And the performance increases were quite substantial, and they found that the code base moving from C++ to something with a bit more concurrency in mind reduced by about 3 times, while the performance went up about 100 times. So designing with concurrency really does provide great scale. So there's, I've talked about Go and I've talked a little bit about actors, which is generally, you see a lot of that in things like Erlang and Java, but there's loads of interesting models. And I think the main takeaway today is definitely try it. There's absolutely loads of great frameworks. I haven't tried all of these, but I've tried to include something for everyone. There's lots of stuff on the JVM here. Java Akka I've tried. This is a great actor framework. Java Quasar is also a similar thing. Scala has actors built into the language. Orleans is the Halo 4 framework that they used for their gaming backend. And Erlang, I think, was one of the first languages to bring it in as a standard part of the language. And CSP is built in to Go, but also you can use the Java Quasar library. Clojure has excellent support for actually both actors and CSP through its core async library, and Scala Gopher library also implements CSP for Scala. And if you want to learn more, these are fantastic talks to go and watch, specifically the top one. Concurrency is not parallelism. That's something that gets confused quite a lot. Thanks very much for listening. I think the one thing to really take away from this is go and try it out. Like, designing with concurrency in mind is just a great thing to do, because it means if you do make something that's really good, and hopefully there's a bit of demand for it, it means in the future it will scale. So yeah, thank you very much for listening. If you've got any questions, come talk to me afterwards.